So let me welcome you all for this session. So today we are discussing about general conduction equation in Cartesian coordinate system. So in order to derive this Cartesian coordinate system general conduction equation, so let us consider first a small element in the Cartesian coordinate system. So this will be the small element in the Cartesian coordinate system, whose dimensions are dx is the length of the element in x direction, and dy will be the length of the element in y direction, and dz will be the length of the element in z direction. Therefore, the volume of the element will be dx, dy, dz. So initially, in order to find the temperature distribution and heat transfer rate in Cartesian coordinate system, no, we need to derive the general conduction equation. Then we will convert that one into one-dimensional equation in the form of differential equations. Then with the help of initial and boundary conditions, we are solving the problem, and we are able to find heat transfer rate equations as well as temperature distribution equations in Cartesian coordinate system. So here in this diagram, if you see now, let Qx is the amount of heat entering into the element. Let Qx is the amount of heat entering into this is a Qx. This is the amount of heat entering into the element in x direction, and Qx plus dx is the amount of heat leaving from the element in y direction. Next one is Qy is the amount of heat entering into the element in y direction. Similarly, Qy plus dy will be the amount of heat leaving from the element in y direction. Qz is the amount of heat entering into the z direction. Similarly, amount Qz plus dz is the amount of heat leaving from the element in z direction. So let K will be thermal conductor of the material. So this is the a small element we have considered in the Cartesian coordinate system, and we are applying the first law of thermodynamics. So if you apply first law of thermodynamics for this system, so we are having, according to first law of thermodynamics, Q is equal to delta E plus W, where Q is total Q will be this one. According to first law of thermodynamics, Q is equal to that will be Q is equal to delta E, that is change in energy plus work done will be there. So here heat will be due to conduction, heat will be generated, heat will be in the element. Next one is heat conducted into the element. Next one is Q, due to flow of current or some or by other means, now heat will be generated into the element. Next one is change in energy plus work done. So here now heat transfer is a process where heat is transferring due to temperature difference only. That's why we are not putting any work. So we are considering the work done in case of heat transfer process is zero. So here this now this is the first element. This is the second element. This is the second one, and this is the third element. So let us find the expressions for a first element, that is heat conducted into the element into the element in all the directions. Next one is second element will be heat generated into the element. Third one is change in energy or increase in energy. So here first we will see the net heat conducted into the element. First we will conduct. So here net heat conducted into the element will be that will be net heat conducted into the element is equal to heat conducted into the element, heat conducted into the element in x direction plus heat conducted into the element in y direction. Next plus heat conducted into the element in y direction plus heat conducted into the element in z direction. So in all the directions, if we add, then only we'll get the total heat conducted into the element. So in order to find the expression for heat conducted into the element, so let us take so Qx is the amount of heat entering into the element in x direction, and Qx plus dx is heat entering into the leaving from the element in the x direction. So Qx plus dx, no, Qx is the entering, and Qx plus dx. Therefore, the amount of heat, the amount of heat with the element will be in x direction will be next one is Qx, and Qx plus dx can be written as according to Taylor series expansion. No, we can write Qx plus dou by dou x of Qx into dx. So like that we can write that. We can neglect the higher order terms because the value will be very small. So finally we'll get the the simplified form will be qx minus qx plus dou by dou x of into qx will be there. So here plus qx and minus qx will be get cancelled. The final simple expression will be minus dou by dou x of qx into dx will be there. So according to Fourier equation, we know that q is equal to q is equal to minus ka dou t by dou x. Since it is only one variable, dou t by dou x along that x direction. So here k is a thermal conductivity, a is a surface area perpendicular to heat flow direction. So in x direction, the surface area perpendicular to x direction will be this is the surface area perpendicular to x direction. This is the surface area perpendicular to x direction. So one length will be dy, the other length will be dy and dz. So the area of the element will be in x direction will be the area of the element in x direction will be, so dy dz will be there. So substituting those values, dou minus dou by dou x of minus k, area will be dy dz. Next one is dou t by dou x into dx. Next one is we are assuming k will be constant and dy dz are constants. Therefore, we can take out of the differentiation. If you take out of the differentiation, you will get dou square t by dou x square into you will get k dx dy dz. So dou square t by dou x square k dx dy dz. So this is the net heat conducted to the element in x direction only. So in other directions we need to approach same procedure. So in order to find the in y direction, so similarly we can derive in y direction. Qy is the amount of heat entering into the element in y direction. So Qy plus dy will be the amount of heat entering into the element in y direction, in leaving from the element in y direction. So finally, after Taylor series expansion and neglecting the higher atom terms, so you will get the simplified form will be Qy minus Qy plus Qy plus dou by dou y of Qy into dy. Here also plus y and minus y minus Qy plus Qy and minus Qy will be get cancelled. Therefore, the remaining term will be minus dou q by dou y into dy. So, according to Fourier equation, now the heat conducted to the element in y direction will be minus k, thermal conductivity of the material, and surface area perpendicular to y direction into this will be dou t by dou y will be there. So, this is the heat transfer equation according to Fourier equation in y direction. So, substituting here, this is ky and ay and dou t by dou y. So, here a means surface area perpendicular to y direction. The surface area perpendicular to y direction will be, so we are assuming this will be the y direction. So, the surface area perpendicular to y direction will be, one element will be, this is one length will be dz, the other length will be dx. So this is the area of the element will be dx into dz. This is the area of that element. So the area of the element in y direction will be, therefore the area of the element in y direction will be dx into dz. Same thing here substituted, dx into dz. So finally you will get dou by dou y of k dou x dx dy dou t by dou z into dz. So if you assume k is uniform throughout the material and dx dy z are constants, we can take out of the differentiation. So finally you will get dou square t by dou y square, dou square t by dou y square into k dx dy dz, k dx dy dz. In the same process, we are finding the net heat conducted into the element in z direction. So in z direction, we will find heat entering into the element in z direction will be qz. Heat leaving from the element will be in the z direction will be qz plus dz. So neglecting the higher order terms, now we are neglecting the higher order terms. Therefore, the value will be qz minus qz plus dou by dou z of qz into dz. So here also plus qz and minus qz will be get cancelled. So finally the expression will be minus dou by dou z of qz into dz. So this qz is there now, That can be written as qz is equal to, according to Fourier equation, minus k surface area perpendicular to z direction and dou t by dou z, dou t by dou z. So finally we'll get this form. So here AZ means surface area perpendicular to z direction. So the surface area perpendicular to z direction will be dx dy. Substituting all these things, you will get dou by dou z of k dx dy dou t by dou z into dz. So since we are differentiating with respect to z, assuming k is constant throughout the material and dx dy are constants, so therefore the simplified equation will be dou square t by dou z square dx dy and dz will be the heat conducted into the element in z direction. Now our aim is to find net heat conducted into the element in a total element. So net heat conducted to the element total element will be, we need to add all the heat conducted to the elements in all the directions. Therefore in x direction it will be dou square t by dou x square. In y direction it will be dou square t by dou y square, plus in z direction will be dou square t by dou z square, and the common term is term is into k dx dy and dz. Same thing is it is written dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square k dx dy dz. This is a common term in all the terms. That's why I have made this term is common across the all the terminology. Therefore, you will get the final equation will be net heat conducted to the element will be dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square k dx dy dz. So this is the heat conducted to the element will be in the element in all directions. Next we will go to the second term. The second term is this is the second term, that is rate of heat conducted into the element, heat rate of heat thermal energy generated in the element. So let small q will be the, we are assuming small q is the heat conducted in the element per unit volume, we are assuming. And for total volume means we need to multiply with the volume. That is for unit volume it is q. For total volume it is q into dx dy dz. So this will be the second element. So next one is we are going for the third element. The third element is change in net energy or rate of increase in net energy within the element. So the change in net energy will be written as mass into specific heat into change in temperature with time. So mass can be written as rho v. Mass can be written as rho v. Mass is equal to density into volume is dx dy dz. Volume is dx dy dz, and the specific heat will be Cp. Change in with the temperature with time will be dt by dt. Therefore, the term will be you will get rho dx dy dz Cp dt by dt. Substituting all this now in the first law of thermodynamics, we'll have that is 1 plus 2 is equal to 1 plus 2 is equal to 3. That is we have seen in the initially. So one is heat conducted element in the all directions, net heat conducted to the element. This is second term is internal heat generated. Third one is change in energy with time, that is increase in energy with time. Substituting all these values now, so you will get in the first law of thermodynamics you will get dou square t by dou x square, this is the first term, plus dou square t by dou y square plus dou square t by dou z square k into dx dy dz. This will be the total will be the first term, and q into dx dy dz will be the second term, and this is the third term. Now what I am doing is dividing the total equation with the common term, that is k dx dy dz. So if you divide the total term means here k dx dy dz will be get cancelled. Here also k dx dy dz will be get cancelled. Here also dx dy dz will be get cancelled. K dx here also dx dy dz cancel. Here also dx dy dz will cancel. Here also dx dy common terms will be get cancelled. Same terms will be get cancelled. Finally, the simplified expression will be dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square q by k is equal to, this will be rho cpk by dt by dt. This rho by Cp by K is called K by rho Cp is called as alpha. Therefore, the where alpha is called as K by rho Cp, it is called as thermal diffusivity. It is called as thermal diffusivity, and therefore the final equation will be dou square T by dou x square, dou square T by dou y square, plus dou square T by dou z square, plus Q by K is equal to 1 by alpha dt by dt. So where alpha is called as thermal diffusibility. So where with help of alpha we can find how fast heat will be diffused into the element. If alpha is very high means K value will be very high, and rho Cp value will be very less. Then in that case now heat will be diffused at fast rate. In other words, when alpha is very less, and it indicates that K is less, and heat stored per unit volume will be very high. It indicates now heat will be diffused into the element at a slower rate. So with help of thermal diffusivity, we can estimate the what is the amount of heat transferred. So this is the general conduction equation. So now with help of various assumptions, we can simplify to various equations like one-dimensional conduction equations and other forms. Let us see how the general conduction equation will be simplified to various forms of equation. So we have seen this is a general conduction equation. In the general conduction equation, so we have seen now dou square T by dou x square plus dou square T by dou z square dou y square plus dou square T by dou z square plus q by k is equal to 1 by alpha dt by dt. First one is first assumption is suppose if heat transfer process is steady state. Steady state means temperature will be remains constant with respect to time. Therefore, the change in temperature will become zero. When change in temperature will become zero, this factor will become zero. So that means the simplified expression will be dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus q by k is equal to 0. The name of this equation is called as Poisson equation. The name of the equation is Poisson equation. Next one is instead of that, if there is no internal heat generation, if there is no internal heat generation in the element means the value of q will become 0. So this value q will become 0. When q is become 0, then what will happen? This is become 0. This total term will become 0, and this term will be there as it is. This will not be there. The final simplified expression will be dou square T by dou square, dou square T by dou y square plus dou square T by dou z square is equal to 1 by alpha dt by dt. So the equation is called as diffusion equation. The name of the equation is called as diffusion equation. So in addition to the if the heat transfer process is steady state heat conduction, and also there is no internal heat generation means then the equation will be simplified as the total equation is simplified as uh, dou square T by dou x square, dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square uh, plus q by k is equal to 1 by alpha dt by dt. So in this now, if heat transfer is steady state means this value will become 0, and also if q is 0 means this value also becomes 0. Then the equation, this remaining equation is there, no, that equation is called as Laplace equation. That equation is called as Laplace equation. So Laplace equation means dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus q by k is equal to sorry, there is no q by k. So this is the equation, it is called as Laplace equation. This is the equation which is called as Laplace equation. Next thing is in addition to the above conditions, now in the general conduction equation, dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus q by k is equal to 1 by alpha dt by dt. This is a general conduction equation. So if the heat transfer process study, we will take this term as 0. There is no internalization, we will take this term as 0. Heat transfer is only in x directions. That means there is no heat transfer in other directions, that these values will become 0. Therefore, we'll get dou square T by dou x square is equal to 0. So this is the equation called as a one-dimensional conduction equation in Cartesian coordinate system. This is the equation which is called as a one-dimensional conduction equation in Cartesian coordinate system. So this is a second order differential equation. So this equation will be solved or integrated twice, so that you will get the temperature distribution equation, and substituting the boundary conditions and other, and with the help of Fourier equation we can derive heat transfer rate equation in Cartesian coordinates also. So with this, I have explained in Cartesian coordinate system how to derive the general conduction equation, as well as how to modify or simplify the general conduction equation into one-dimensional conduction equations. So thank you one and all for listening this session. I hope this session will be very much useful for you. You can drop your feedback on comment section. Thank you.